Well, today we have in the seminar, we have Edmund Heng from the IHES, who is going to talk about fusion categories as quantum symmetries on the Bridgeland stability condition. So,
Yep.
when you're ready, Edmund.
Okay, sure. Thanks. So thank you for the invitation to speak here. I've personally never been to Argentina actually, but it will be great if at some point I would like to visit. So okay. But I'm gonna talk to you about fusion categories as quantum symmetries today. And the point is that the first picture that I want you to keep in mind is that you should think of this as some sort of like a generalizations of groups, in particular finite groups in these cases. But your actions are no longer going to be invertible. And I'll get to the point where I explain what this really means. But that's the rough picture that you should have in mind, which is fusion categories. Their actions are meant to generalize finite groups. Okay, so also I should quickly say that whatever that I'm going to talk about today is going to be a combination of joint work with Hannah Dell, Ben Elias, and Anthony Licata. Okay, so let me just begin with abstract nonsense, which is just the definition of a fusion category. So for my talk, every time when I write K, it's going to be a field which is algebraically closed. I don't really need characteristic 0 for most cases, but the main thing that I really need is just the fact that it has to be algebraically closed. Okay, so what is a fusion category? So a fusion category is going to be an abelian category, which is semi-simple. So somehow as an abelian category is really trivial, like there's nothing interesting about it. So it's just a abelian category, which is semi-simple, and it's also k-linear. And what I mean by that is that my Hom spaces, so my morphism spaces between my objects is always going to be linear over the underlying field. So they are vector spaces. But what's going to be interesting about this is not really the abelian structure, but the monoidal structure. So it's going to be equipped with some sort of tensor product structure called the monoidal structure, such that I have the following assumptions, which is my monoidal unit. So you should think of this as like 1. So the object 1, which tensor by anything just goes back to itself, has to be a simple object, right? So in the abelian category, it has to be a simple object. And moreover, every object has left and right dual. So what I mean by this is going to be as follows. So I want that if I take my object X, okay, it has a tensor product structure, right? So X tensor blah is always going to be a functor from C to C. All right. And having left and right duals means that I have another object, which I'll call dual X, which again has a tensor product structure induced by the tensor product structure, gives you a functor again from C to C. And being left dual means that these two functors here are left adjoint. So this is left adjoint of this. Okay, so this is left adjoint of this. Okay, so that's what it means to be a left dual. And similarly for right dual. So you have a different object, right, which usually I'll denote by X hat, and the tensor product structure induces the right adjoint of the functor. Okay, so that's what I mean by having left dual and right dual. Sometimes this property is also called rigid, but maybe in finite dimensional algebra it kind of clashes, so I will try and avoid using that word rigid. Okay, and finally the last assumption that I'm going to make is that my category is always going to only have finitely many simples. Okay, up to isomorphisms, I should say. So what I mean by this is that as this is more like an abelian category structure, that there's only finitely many simple up to isomorphisms in my category. Okay, and maybe just for notation purposes, for today, I'll always write irreducible C to mean like, just a set of choice of representative of my simple objects. Okay. Okay, so this is just the abstract nonsense of what a fusion category is. But really, it's probably easier if we just stick to examples and see what fusion category contains. So one of the first examples that I want you to keep in mind is the category of finite dimensional vector spaces, which are also graded by a finite group G. Okay, so G is going to be a finite group and it's G graded. So what do I need? So how is this a fusion category? So first of all, being just vector spaces and G graded vector spaces, this category is a semi-simple category, right? All objects are just up to direct sums, just G graded. vector spaces. Okay, and in particular, what are the simples? The simples are just going to be the one-dimensional vector space where my one-dimensional vector space sits exactly at degree G. So each of these is a simple object, right? And maybe I should also quickly mention that by G-graded vector spaces, the morphisms that I'm looking at needs to be G grading preserving as well. So only G maps to G, hence the semi-simple structure. So the simple objects are just the one-dimensional vector space where the one-dimensional vector space just sits in the single degree G. Okay, and this is how, by abusing notation, I'm just going to write this as G. Okay, so these are the simple objects, and as you can tell now, every object is in my G-graded vector space category is just going to be a direct sums of these simple parts. Okay, and moreover, what is the tensor product structure? So what is the monoidal structure? Well, you're just gonna multiply them, or if you like, just tensor them according to how the group multiplies. Okay, so it's just gonna be according to how the group multiplies.
Excuse me.
Yep.
Quite confused with notation G graded. So G is some group that appeared or.
Yep. So for any choice, so maybe I should just say that this G here is any finite group.
Finite group. Okay.
Any finite group G. Yes. Yeah, it needs to be finite.
Or compact.
Not for this talk, but some sort of generalization you could do that. But for this talk, I want a discrete finite group. Yeah. Okay. All right, so where were we? So the monoidal structure. So the monoidal structure of my category is just going to be induced by the group multiplication. And in particular, the dual objects, so the left dual and the right dual are just going to be the same object, and it's just the inverses, right? Because that's if you check, that really equivalences are always going to be adjoints. And so in this case, you just use that. Okay, so this is the first example. And maybe in the simplest cases possible, which is when your group is the trivial group, right? So just the group with a single element, then vec G is just vec. Okay, and that's the simplest possible fusion category, in fact. Okay, so that's the first example. So what's this next example? So the second example is just going to be the representation category of the group. So my representation category of my group. So this is the first part. I'll need to assume that my characteristic does not divide my group, the size of my group. And once you have this assumption right here, then we know that the classical theorem will tell us that this category is indeed a semi-simple category. And the monoidal structure is just the usual tensor product of representations. And the dual, so every object does indeed have a left dual and a right dual, which again is isomorphic because you just take the dual representations. Okay, and that's the second example. All right, so lastly, so these two examples are kind of like vector spaces, at least the underlying objects are really vector spaces. And I'm just going to throw you one more rather exotic example, which the fusion category is going to be something that kind of behaves like a golden ratio thing. So what I mean by that is that this category is usually denoted by fib, or sometimes also called golden ratio category. But as a semi-simple abelian category, it's very easy to describe. It has exactly two simple objects, one which I'll denote by 1, and the other one I'll just denote by pi. And you should think of this object 1 as the monoidal unit. So indeed, this has to be the monoidal unit. But this object pi here is kind of like a golden ratio object. So what I mean by that is that if I take my object pi, and under this monoidal structure, the tensor product is going to decompose into 1 plus pi. Okay, and this is why it kind of behaves like a golden ratio, because this is exactly what the golden ratio is going to satisfy. Okay, so this is rather exotic. I won't tell you how to construct. So first of all, this monoidal category does indeed exist, and you can really write down the datas. If you want to, you can kind of construct it as like a sub-fusion category from those associated to UQSL2. But the point being that it exists and is in fact is actually also known to be unique. So, but the main takeaway that you should have for this particular example is just that it is a monoidal category that satisfies an equation that looks like this. Okay. All right. So these are the three examples, or at least three family of examples I want you to keep in mind. Okay, so let me now slowly formalize what I mean by having a fusion symmetry. So just as how group acts on categories, you usually say that it's like you define some sort of action by defining from your group into the auto-equivalences or into the whatever, depending on what objects you're acting on, you map it into the symmetries. So here is going to be very similar. So all that I want is that I say that a module category M over C, okay, or equivalently, I'm just going to say C acts on my category M. It's just going to be consist of the following data. So for this particular talk, I'm going to only look at categories M, which are either abelian or triangulated. You can kind of change this according to what you want. So really, again, it just depends on what kind of categories you would like to act on. But for my talk today, I'm just going to focus on either my category that I'm acting on is always going to be either abelian or triangulated. And by an action, I just mean giving me a monoidal functor from my fusion category C into the category of Endel functors. Okay, so let me just note here quickly that this is the monoidal structure here is given by composition. Okay. Okay, so the monoidal structure here is given by actual compositions. And all I'm asking for is just a monoidal functor from my fusion category into Endel functors. And because I'm focusing on abelian categories and triangulated categories, I'll also add in the fact that I want them to be exact. Okay, so it means to preserve the structure of my category. Yep, sorry.
The word monoidal there is strong monoidal.
Monoidal in the sense that strong monoidal, yes. I don't want to involve any higher structures. Yep.
Thank you.
If you want to, I think you can even think of this as let me see if I can get this right. So you can upgrade C into a 2 category with a single object, if you want to. And you can, and what I want to have a monoidal functor means that I have from this 2 category with a 2 category with a single object, and now my one morphisms are objects in my fusion category. It's going to be defining a monoidal functor is the same thing as defining a 2 functor from this 2 category that I've cooked up into the 2 categories of cat, or in this case maybe either abelian or triangulated, and that's what I mean as well. So it's going to be equivalent in that sense. Yes.
Thank you.
Okay. All right. And okay, so this is what I mean by a fusion category acting on a category, or equivalently also usually this term is used as we have a module category over our fusion category. Just the term module category should be thought of as something like your fusion category is like your ring and your module category is like your module. And that's why the term module category was introduced. But for today's purposes, I kind of want you to think of it as really we have like a ring acting on a module. So here a fusion category acting on the module category. Okay, and just finally for notational purposes, I won't really write psi x every time to denote the functor. I'll just abuse notation and always write x tensor blah. Okay, so given the fusion object in my fusion category x, it's assigned to a functor, and the functor I'm just going to denote as x tensor blah. Okay, this is just notational purposes. Okay, so just a few remarks. So as you can tell, like the fusion categories that I showed you just now, for example, the representation category of a group, the tensor product is not invertible. Because if I just give you any representation of higher dimensional, which is any representation of a group which is not one dimensional, then the tensor product can never bring you back to the trivial representation, which is one dimensional. Because nothing, if you like, there's no half dimension or any rational number which is not just integral dimension. So I can't divide and just go back to a trivial representation. So the functors that I'm going to assign to it's definitely no longer going to be an equivalence. So if my object was not invertible, then the functor that I assign to might not be invertible. But remember that we always have a left dual and a right dual. And what this means is that being a monoidal functor, going from my fusion category to Endel functors, it says exactly that any kind of functor that you assign to, so this functor here always has a left adjoint and a right adjoint. Okay, and indeed, like if you want to throw away equivalences, the next step, the next weakening that you can do is to look at functors which has both left and right adjoints. okay? And having this kind of tells you a few things. So for example, this function here is always going to preserve projectives and injectives because they're both left and right adjoints, okay? And moreover, in fact, like if you actually had M just to be an abelian category and you only ask for assignment of functors which are additive, then exactness actually falls for free, again, because of the left and right adjoint property. So, but mainly, maybe just to keep in mind, it's just that it actually preserves, for example, projectives and injectives. Okay, so these are all of the abstract nonsense. And now I'm going to show you some examples. So where do like categories like this and where do fusion symmetries actually show up? So the first thing that I wanted to convince you was that fusion categories is indeed a generalization of G action, of group actions on categories. So let me quickly remind you what I mean by group action again. So group action on a category M is going to just be an assignment for each of my group element here to some autoequivalence of my category M, okay? And which I denote by theta G. And moreover, I need to tell you that it acts according to, it respects the group multiplication structure, right? So it says that if I compose theta G and theta H, then it needs to be isomorphic to theta GH, okay? And having a group action on a category, this is not sufficient. I mean, usually in sets, this is enough, but in categories, you have extra structures. So you want to also understand the morphisms. So in particular, these isomorphisms here need to be natural. And what I mean by that is that it also has to satisfy an associativity structure, meaning if I compose theta G, theta H, and theta K, I have two ways of getting into theta GHK, all right? And I want to say that if I first compose these two, and then compose G with HK, then it needs to be the same as if I first compose GH and then compose K with GH. These two things need to be equal, okay? So this, maybe in this sense was the one that you were asking whether or not it's strong, and I want it to be equal. So this one really needs to be an equality, okay? Not just up to some sort of two morphisms that they're the same. Okay, and so this is what I mean by action. Sometimes it's called strong action, but really I just want to call this a group action. Okay, so why do I say that a G action is the same thing as a fusion category action? So in particular, if you now look at the fusion category vec G, all right, so given G here, sorry, I should also again say that G here is always a finite group. So maybe just to put it out there, every time when I write the word G, it's always going to be a finite group. We can discuss more about local compact groups later on if you want to, but G for the time being always going to be a finite group. So if given a finite group G acting on M, you can now instead view it as an assignment from the fusion category vec G. Remember, this is the category of G-graded vector spaces into the endofunctors of M. All right, into the endofunctors of M. And the assignment is, again, G here now is no longer a group element, but the one-dimensional vector space with a single degree, concentrated in a single degree G, right? And I also assign this simple object into theta G. Okay, so and this is just some assignment of functor. And why is this actually a monoidal functor? Well, the fact that it's monoidal falls exactly from this square that we had up there. Okay, so really G action on categories is exactly the same as monoidal functors from vec G into endofunctors of M. Okay, so that's the first picture that you should have in mind. So indeed, action of fusion category does exist if you just look at just groups. Okay, so this is like back to the classical case, if you like. All right, so maybe this is less interesting because we're just doing the same thing with groups. So why do I care about fusion categories anyway? So here's one question for you. So given this quiver here, if you like, this is like just like a bipartite A4 quiver. Maybe spend like 5 seconds or 10 seconds thinking about what kind of auto-equivalence of this quiver do I have? So what kind of symmetry do I have on this quiver? And maybe more importantly, what kind of symmetry do I have on my representation category Q? Okay, so maybe let's just quickly look at this quiver here. This vertex has two arrows going out. It's a source and has two arrows going out, but this one is a source with a single arrow going out. On the other hand, this is a sink with a single arrow, and this is a sink with the two arrows. So at least you can tell quickly that the automorphism of a quiver is just trivial. I can't do anything because they are sink and sources of different number of arrows. And really, you can even check that, in fact, autoequivalences of RepQ is going to be isomorphic to just a trivial group. Okay, so there's indeed no classical, if you like, there's indeed no group symmetries and no classical symmetries of this category of RepQ. But my claim is that there's actually interesting fusion categorical actions on RepQ, where Q is this A4 quiver right here. And my claim is that the real golden ratio category that I showed you just now actually acts on this representation category. So to show you how it acts, I'm going to do a slight detour, hopefully quick detour, and introduce a different category with a very obvious action of the Fibonacci golden ratio category, and see how it actually translates into the A4 quiver. So let's fix C to be the fusion category flip. And I'm going to define like some sort of like a quiver-like representation category twisted by this golden ratio object pi. And so this category is going to be defined as follows. So my objects are going to consist of a tuple, right? So think of quiver representation. How do you define a quiver representation? To each vertex, you attach vector spaces, and then to each arrow, you attach a linear morphism between vector spaces. So by this here, I'm just going to do something similar, which is instead of putting vector spaces, I'm going to put Fibonacci objects instead. So objects in my fusion category flip. Okay, so it's going to consist of a tuple where in the first vertex here, I put some object V1 that is in Fibonacci. And similarly, on the second vertex here, I just put some object V2 in my Fibonacci category. But what this pi here is telling me is that instead of taking the morphisms from V1 to V2, I'm going to twist it. I'm going to twist my morphism by first applying pi tensor by V1 and then mapping into V2. Okay, so if you like a representation of this quiver, which sometimes called fusion, which is what I would call fusion quiver, it's just going to be a morphism from pi tensor V1 into V2. Okay, so this is just going to consist of such a data. So very close to representation of quiver, but it's going to be twisted by the fusion category that we have. And morphisms is going to be something similar, which is I'm going to give you a morphism between V1 and W1 and between V2 and W2. And I want the usual square to commute. In particular, I'm not allowed to touch this pi part. Okay, remember the twisting is part of the structure already. It's not something that you give. It comes with the definition. So I'm only allowed to give F1, which is a map just from V1 to W1, and a map from V2 to W2. And I want this square to commute with respect to this, with respect to the fact that I'm not touching the pi part. Okay. All right. So my first claim is that you can quickly check, just as how you would check that the representation of quivers is actually an abelian category, that this is also an abelian category, where what you do is you take vertex-wise kernel and co-kernels. So remember that your Fibonacci category, or any fusion category, in fact, is going to be an abelian category and also semi-simple, importantly. So you can just take kernels and co-kernels in the same way as how you would take kernels and co-kernels in FIB. So you take kernels and co-kernels with respect to the abelian structure given by the Fibonacci category. Okay. All right. So what's important is that actually not just that it is a fusion, it is an abelian category. I claim that it's actually also naturally an abelian module category over FIB. So if you like, I have a very natural action of FIB on this category. And what do I mean by this? I just say that I'm gonna, every time when I'm given a representation which looks something like this, right? It's V1, V alpha, and V2 that maps along these two objects. I can tensor, take any object in my fusion category from FIB and just tensor on the right-hand side. Okay, tensoring on the right-hand side gives me a new object that looks something like this. And why is it a representation? Well, on the first vertex, I'm just attaching V1 tensor pi, right? And on the second vertex, I'm attaching V2 tensor pi. And now my morphism is just going to be given by V alpha that I had just now, tensor with the identity on pi. Okay, so it should be pretty clear that this is actually a functorial definition. and I'm just acting on the right-hand side. Okay, and this defines a monoidal functor which assigns every object in Fibonacci by tensoring on the right-hand side. Okay, and that defines the functor. Okay, and so in particular, I'll just quickly say how. So back then, for example, how do you check that the simple objects of my quiver is just concentrated in a single vertex and zero everywhere else? It's going to be the same thing here. So, but although it looks like we have two vertices, my first claim is that there's actually 4 simples in this category. So why is that the case? Well, mainly just because on each of these vertices here, I can put more than 1 simples, right? Because my Fibonacci category has 2 simple objects. So on each of these vertex, I can attach 2 simples, either 1 or pi. Okay, and so that gives me 4 types of simple. So concentrated in degree in the first vertex, I can put 1 or pi. Concentrated in the second vertex, I can put 1 or pi, and that gives me the 4 simples. Okay, and moreover, as you can see, if I use this structure of Fibonacci acting on the right-hand side, the 4 simples are related as follows. So this simple here can be sent into this simple by just acting by pi on the right-hand side. And now if I act on this again, it's going to split up, right? Because this is going to give me, if I act by pi again, it's going to give me the direct sum of 1 to 0. So this is one of the representation. Direct sum with pi tends to pi to 0. All right, so now it decomposes. And in fact, this should be exactly reminiscent of the fact that pi tensor pi is 1 direct sum. Okay, so you should think of this as from this part, if I do pi twice, I should get 1 copy of myself and 1 copy of what I'm acting by just doing it once. Okay, and this is how the simples are related. Okay, so how is this rep A4? So in fact, you can kind of compute this by hand if you want to, but you just have to trust me that this is the case. We have exactly 4 simples, and I'm just gonna label them according to what we have. If I label my vertices of A4 in this case. So this is going to be S1, this is going to be S4, this is going to be S3, and this is going to be S2. But maybe the easier way of thinking about this is that you should kind of think of this first vertex here as like 1, this is pi, and this is 1. Okay, so in particular, if my first vertex I've attached 1, then it's just going to be this vertex. Okay, it's just going to be simple according to this vertex. And similarly, if on my first vertex I attach pi, then it's just going to be a simple on this vertex here. Okay, at least on the simples, you can really just check by hand in this way. But the projectives and the injectives and in particular the pre-projective or pre-injective objects can all be computed, and they correspond. They are exactly in one-to-one correspondence this way. And in fact, you can prove by doing some work that these 2 categories are actually equivalent as abelian categories. So what you can do now is that, okay, well, I have a natural Fibonacci category action on this category, okay, which looks slightly exotic to begin with, but instead it actually helps you define like a Fibonacci category action on the good old A4 quiver, right? Which we saw that there's no classical symmetry, but actually there's a interesting Fibonacci category action acting on it. Okay, and this is how it acts according to the AR quiver. But maybe this is actually, let's see what I want to say next. Okay, so just a short remark that you can actually study quivers that looks like this, meaning just usual quivers, but now my arrows are also labeled by objects in my fusion category, and study the representations in the same way. And you can also classify them, meaning classify the finite type representations. So when is rep of this fusion quiver going to have finitely many indecomposable objects? And this is you can show that actually it is in one-to-one correspondence with the Coxeter-Dinking diagram. So not only the ADE ones, but instead like the BCFG and also the weird non-crystallographic types H and I also shows up. And this is what I showed with Ben Elias. And I won't go into too much details about this classification or this kind of the representation of this kind of quivers today, but just letting you know that the studying quivers of this form also has like a very nice classification result. Okay, and in fact, if you know slightly more about gentle algebras and maybe something about Fukaya categories, then the picture is also pretty nice. So you can every time when you have a gentle algebra, you can cook up some sort of like a topological Fukaya category, and the derived category of your gentle algebra is going to be equivalent to this Fukaya category. And in particular, in this case, it's even more beautiful because what it tells you is that the Fukaya category is going to be the Fukaya category associated to a pentagon, and your objects sitting, which I've boxed out right here, is going to be exactly lying outside the edges. So it's going to be the outer edges of this pentagon. And if this was actually a regular pentagon, some geometry is good. You can compute something which says that, well, if this is length 1, then this is actually a golden ratio times that length. Okay, so this is going to have golden ratio length. So if this has length 1, this is going to, any of the inner edges is going to have length golden ratio. And in fact, this is how the action is going to act. It's going to take any outer object and it's going to send it to an inner object. Okay, and then the inner object has a split because of the golden ratio relation. But it always takes the outer object and pushes it parallelly into the diagonal objects. Okay. All right, so maybe all of this, I have to admit that all of these are probably quite exotic. I mean, I'm giving you some, either we're just looking at the classical case where we just have groups acting on good old categories, or I've showed you some weird fusion categories which somehow acts on well, okay, potentially familiar categories.
Man, it's gonna have a stupid question about
Yep.
the first picture. Yeah, so on the left we have the A2 quiver, right? And when I see a pentagon, I think immediately about the cluster algebra of type A2.
Mm-hmm.
Is it related?
I believe this is not really the cluster algebra of type A2 because, okay, so I believe what you need to do is as follows. You kind of need to, you need to talk about the frozen vertices as well. And once you add in the frozen vertices, I believe this should be the picture of, it should be the A4 picture. It should still be, the quivers should still be A4, but here I've kind of thrown away the frozen vertices, if you like. So there should be like a bigger picture that kind of sits here, if that makes sense.
Okay.
And there should be like frozen vertices here. And also note that I'm not taking the Calabi-Yau completion, so I'm just taking the good old representation of the quiver. So if you like, if you want to do the Calabi-Yau picture, I'm taking a bigger n-gon, so it should be the 10-gon here. And I've thrown away the outer ones. I've thrown away the frozen vertices. So it should really be a A4 picture.
Okay, thank you. Interesting.
Yep. Okay, good. All right, so let me hopefully so I'm going to show you one last example, and hopefully this will be slightly closer to heart. So once again, let's go back to the case where we have a group action on an abelian category. Or okay, well, okay, for this case, let's just focus on abelian. And starting from a group action on from this category, again, I want to remind you that vec is the same thing as saying that we have a vec G acting on M, okay, or M being a module category over the G-graded vector spaces. So what one can do from this kind of data is to construct the G-equivariant category, okay? So instead of giving you the definition first, I want to give you examples so that you have something concrete to think to keep in mind. Is that, for example, if you have a finite dimensional algebra A with a group acting on it, then what you can construct is always known as is something known as the skew group algebra, right? Where your multiplication is twisted by your group action, okay? And the G-equivarentization category, so the G-equivarentized category is just going to be the equivalent as abelian categories to the modules over the skew group algebra, okay? So that's the first example that I want you to think about. So every time when I say the word G-equivalent category, it's just going to be the same as the skew group algebra in the algebraic world. Or if you're more of a geometer, then I'll just say that, well, if you have some sort of variety or a nice scheme with a nice group action on it, then you can study coherent sheaves, and the G-equivalentized category is just going to be exactly the G-equivalent coherent sheaves. Or in nice cases where a group action is free, then this is really an honest quotient, and it's the same thing as studying coherent sheaves on the quotient. Okay, so this is the concrete picture that you should have in mind. But the construction of a G-equivalent category is as follows. It's basically a categorical construction of the fixed points. So because if you just take a group action acting on a category and you look at the subcategory generated by the fixed objects, it's not going to be a nice category. But if you add in certain extra data, meaning keeping track of the isomorphisms as we'll see soon, then it's going to turn into a nice category. And in particular, if your category was abelian to begin with, then the equivalentized category is always going to be abelian as well. So how do you construct something like this? Well, your G-equivariant category, which I'll denote as m to the power G, can be constructed as follows. Your objects are going to be your objects from your original category m. But now I want to attach to these kind of objects bunch of isomorphisms data, meaning I'm only looking at object X, which are fixed by my group action, all right? Hence this isomorphism here. And I want to each of these G, I want to attach such a data. And moreover, I want them to commute, just as how you had previously. So I don't just want fixed object, but I want fixed objects whose isomorphisms can all respect each other nicely. Okay, and the morphisms is going to be straightforward because all I'm going to have is just morphisms in my original category M, such that it commutes with the isomorphism data. Okay, so this is how you construct it categorically. And again, if this confuses you, just think about skew group algebras in the algebraic case, or just G-equivalent coherent sheaves in the geometric case. All right. So my first question for you is that, okay, so we started off with the category with a G action, and now I've taken the equivalentization. So what really acts on this category MG, right? So in some sense, I've killed all of the interesting symmetry coming from my group G. What's left? My claim is that actually the representation category acts very naturally on this category. For the skew group algebra case, I'll leave it as an exercise for you to work out how. But using the categorical group construction, you can work out that all it does is that it takes a representation of my group, which consists of V, which is the vector space that I'm acting on, and bunch of data of G power Gx, and it acts on my equivalentized category by just saying that I'm taking V copies of X, and I'm just acting according to how the matrix originally acts with these isomorphism data plugged into it. Okay, so I just create a bunch of copies and then just attach the matrices with Phi in it. Right? And this defines a monoidal functor from rep G into the endal functors of Mg. Okay, well, whatever, right? So I mean, I've given you so many examples, but why should you even care about this kind of category actions after all? I mean, sure, they are there, but what can you use it for? So my general slogan is going to be something as follows. Anytime when you have a G action on a category and you wanted to study G-invariant problems for your original category M, the equivalent problem in the dual side, meaning for your skew group algebra or in more general for the G-equivalentized category, the equivalent problems that you should study are actually rep G-equivalent problems. Again, whatever that means. But I'm going to make it very explicit in the following case. In particular, in the case of stability conditions. So just some background. Here, D is going to be a triangulated category, and G is just some actions on the triangulated category D. And what Macri, Morita, and Sterol showed is that for each of this triangulated category D, we can assign what is known as the Bridgeland stability manifold. So this is some sort of complex manifold that one can cook up from the data of triangulated categories, and it forms a complex manifold. And one can look at the fixed points of this group action. Okay. And what Macri, Morita, and Stellari showed is that there is actually a close embedding from the G fixed points of my original category, stability conditions of my original category D, into the complex manifold of stability conditions for the G equivalentized category. Okay, there's a close embedding of complex manifolds in this case. So the very natural question to ask is that, okay, can we actually identify the image of this embedding? So in the case where my group is actually abelian, right? So when my group is actually abelian, then Perry, Pertusi, and Zhao independently with my co-author, one of my co-authors, Hannah Dell, has shown that if G is actually abelian, then the image is exactly the G hat fixed points, right? The G hat fixed points in my G equivalentized category. Okay, and G hat here is just the Pontryagin dual, or if you like, just all the one-dimensional representations, which is the point of view that I prefer. So as you can hopefully quickly realize, is that when G is abelian, then all of your representations are one-dimensional. And indeed, this here is really just writing rep G. I mean, maybe with slightly less structure, but this is essentially the same thing as writing rep G. So moreover, you can check that, well, once your group is not abelian, you can quickly find that this dimension is too big. Like only looking at the fixed points of this Pontryagin dual is way too big to be the image of this close embedding. And in fact, really what you need is that you need the whole structure of rep G. To find out what the image is, you need what is known as this rep G equivalent stability conditions, which is something that I'll introduce quickly in a few minutes. Okay, so again, the slogan is that if you want to go from M, your original category with the group action G, to the dual picture, meaning again the skew group algebra, or it's going to be the G equivalent category, and you want to study problems there, you really need the whole rep G structure. You can't just use, for example, the Pontryagin dual. Okay, so this ends my motivation in some sense, and bunch of hopefully enough examples for you to keep in mind what kind of fusion category actions we have. And the main theorem that I'm going to show you today is this homeomorphism here, which is the space of G invariant stability conditions on my original category is going to be homeomorphic to the space of rep G equivalent stability conditions on my dual category, which is the G equivalentized category. All right. And I'll explain what this really means. Okay. So let me just quickly remind you what stability functions on abelian categories are. And so from now on, A is just going to be an abelian category, and a stability function is just a choice of my group homomorphism from my Grothendieck group of my abelian category into the complex number, such that all of my objects, all of my non-zero objects, live in the upper half plane and potentially negative real numbers. Okay, so maybe for those of you who know a bit more about Rudakov work or king stability, let me just quickly mention that this stability function is essentially the same one as the one studied by Rudakov, but slightly more general than king stability. Okay, and in this case, what I can do is that I'm going to every object E, I can assign what is known as the phase of my object with respect to this stability function Z. And it's just going to be the argument of Z divided by pi. This is really just a normalization. You can ignore this if you want. But point being that it's going to live in 0 to -1. Sorry, from 0 to 1. Okay, and 1 included, but 0 not included. So again, the picture that should have in mind is that I'm allowed to map to anything here, including the negative real line, but not the positive real line. Also not including 0, by the way. Very important point. You can't map any object into 0. Okay. All right. And I'm going to say that an object is semi-stable if my phase of any sub is less than or equal to my original object. Okay. This should hopefully remind you, if you know a little bit more about stability of vector bundles, this is basically the same definition, right? And we say that this stability function satisfies what is known as the Hn property or the Hagen-Arison property if there's always a finite filtration such that each of my sub-quotients, right? Each of my sub-quotients right here, is going to be a semi-stable object where my phase is always decreasing. Okay, decreasing from left to right. Right. In particular, if your abelian category was actually already in the Therian or Artian, basically finite length to begin with, then this always holds. So you can kind of ignore this property if you want to. Okay, so these are stability functions on abelian categories, and let me just quickly say how you should think of it. So for example, just take the representation of the A2 quiver. Then a stability function would just look like an assignment like this, right? Everything into the upper half plane in this case. And my first simple is going to go here, and my second simple is going to go here. And the image of P1 is going to live here, right? Because it's just S1 plus S2. All right. And so in this case, you can actually always convince yourself that simples are always going to be semi-stable, right? Because there's essentially no sum, so nothing to check. But in particular, in this case, remember that P1 is the projective at 1, so it has sub the simple object at 2. Okay, and it is indeed semi-stable, and in this case even stable, because the phase of S2, right, is lower than the phase of P1. Okay, so P1 here is semi-stable. All right. But what happens if I swap? What happens if I swap around the order? Meaning now instead I put S2 here, but S1 here. So I've now increased my phase of S2 to be strictly greater than S1. Well, in this case, P1 is no longer semi-simple, right? Because as we can see, my sub-object, which is S2, sitting inside P1, actually has a greater phase, right? And moreover, remember that the Harden-Arrowsmith filtration that we had just now, meaning bunch of subs such that each of the sub-quotient is actually semi-stable, looks exactly like this. So this is the filtration. I have P1 sitting inside S2 and 0 sitting inside S2. And the quotient of S2 by P1 is just S1, which is semi-stable of this phase. And I have 0 quotient by S2, which is just S2, which has a higher phase than S1. And so my phase goes from S2 to the phase of S1, which is decreasing. And this is the Harden-Arrowsmith filtration. Okay. All right. So this is this. So in some sense, you can think of this as abelian stability functions buys you like a finer filtration than the usual filtration, for example, given by the Jordan-Holder filtration. So I should say that the Harden-Arrowsmith filtration, so this kind of filtration by sub-quotients which are semi-stable with decreasing phase, is always going to be unique. Whereas the Jordan-Holder filtration, for example, is going to be unique only up to permutations of the symbols that shows up. Okay, so this is what it roughly buys you, if you like. So what about triangulated categories? So in the end, I want to work with triangulated categories to talk about this bigger complex manifold. If you don't know what a triangulated category is, I'll just say that you should just think of derived categories of your favorite abelian category. So derived category of finite dimensional modules over finite dimensional algebras, for example. But a stability condition on a triangulated category just consists of 2 pieces of data instead. So first of all, you need to give me a heart of a stability of my triangulated category. So this is some sort of subcategory in my triangulated category, which is an abelian category as well. So in particular, if the triangulated category that you had in mind was the derived category, then a very natural heart to pick is exactly the abelian category you begin with itself. All right, so you need to pick a heart, and then you pick a stability function on it. Okay, so note that the Grothendieck group of your heart is always going to be isomorphic to the Grothendieck group of your triangulated category D. So that I won't really make a difference between these 2 things. I'll always think of them as the same. And for technical reasons, you need to make sure that this stability function has the Hn property. Otherwise, things don't work. But again, if the heart that you're thinking of was already like Noetherian or Artinian to begin with, then this is superfluous. You don't need this. Okay, so remember, abelian categories, a stability function is just some sort of choice living in the upper half plane or the negative real number. And for triangulated categories, once you upgrade it to triangulated categories, you just need to also tell me which heart I'm doing the stability function with respect to, and then that's it. Okay. All right. So in this case, what can we do? So if we started off, so just now we saw the picture for representation of the A2 quiver, and now I'm going to upgrade it to derived category. And the point of doing it in the derived category case is because you can kind of deform the stability function locally, which cooks you up new heart. And that is a moduli space. And that's the big picture. So suppose we started off with a stability function that looks like this. Everything just lives in a negative real line. I can locally deform, so just push S2 slightly upwards. Right? Epsilon here should be taken as very small. Push it slightly upwards. And this is now a new stability function on the same heart. On the heart rep S2, rep A2, okay? And this is now the picture that we saw just now, which is the case where P1 is actually semi-stable. But you can now ask the question, what happens if I now push S2 downwards instead? This was not allowed in the abelian category case, right? Because we said that everything needs to go into the upper half plane, or at most, the limit point would be the negative real number. But instead, if you do this, what Bridgeland tells us is that actually there's a unique heart which is close by with respect to some sort of distance that you can cook up so that this, with respect to this new heart, you still have a stability function. Okay, and this is exactly the heart that you should be doing. If you know more about tilting, then this is exactly just a tilt at a symbol. And in this case, you can see that P1 is no longer in the heart, but P1 has a heart filtration given by this this new heart in such a case. All right, and that's really the main theorem of Bridgeland, which says that the space of stability function conditions for my triangulated category, if I consider the forgetful map into just the stability functions, all right, so just the group homomorphisms from K, from my growth group of my triangulated category into C, this map is a local homomorphism, meaning if I map it down, I locally deform it, I can uniquely lift it up to a heart, which corresponds to this stability function. And in particular, this gives my space of stability condition a structure of a complex manifold. So I should say that there's a way to put a very natural topology on step D, and that makes it into a complex. This local homomorphism here makes it into a complex manifold. Okay. All right. So what happens if we have a G action on my triangulated category instead? Then, well, instead of looking at all possible stability conditions, you can look at the fixed points. And by fixed points, what I mean by this is just as follows. My heart is going to be close by my G action. And in fact, because G is invertible, this is actually an equality. But all I'm going to ask for is just my heart is going to be close under my group action. So if you like, we start off with a bigger triangulated category D, and it restricts to an action on the heart. And my stability function is going to be invariant under my group action. So what I mean by this is exactly this equation right here. So if I start off with an object X, I look at the stability function of it and compare it with the stability function on G acted upon X. They need to be the same value. They need to hold the same value. All right. And this is exactly the same thing as saying that I want to fix points of my group action on the Hom spaces defined appropriately. Okay. And one little remark that I'll just quickly mention is that knowing that your stability function is G invariant is not sufficient to guarantee that your heart is actually close under the action. In particular, I can't just take my local homomorphisms that I had just now, look at the subset of G invariant stability functions, and then just do the pullback, just lift it back up and see what it is, and call that the G invariant stability condition. That is not the same. Okay. In general cases, when it's a covering space, sometimes it's even just like some particle connected component, for example. So it's definitely not something, it's not trivial that for this particular theorem that I'm going to tell you, which is again shown by Morita and Stellari, that the space, the subset of G invariant stability condition, so the subset of this kind of stability condition, the fixed points, is indeed a local homomorphism into the stability functions which are G invariant. Moreover, as a topological space, step G is actually closed inside this whole space of all stability conditions. Hence, in particular, this whole space of stability conditions which are G invariant actually forms a closed submanifold of my whole complex manifold, step D. Okay, and this is the big theorem by Morita and Stellari. And to prove this theorem, actually, if you know slightly more about the symmetries of space of stability condition, it's actually not too hard to show, because all you need is the following lemma, which only talks about abelian categories anyway. And it's going to be as follows. It says that if I have some abelian category, H, all right, with, again, a group acting on H, then I can only ask, so again, I'm just going to only ask for stability functions which are G invariant, right? So again, what this means is that I'm going to look for stability functions which I had exactly, that look exactly like the points where it's acted upon by my G action is going to go to exactly the same place. Then it turns out that the following is actually equivalent. If an object is actually semi-stable with phase theta, so with a particular angle theta, then any other object acted upon, any object G acted on X, okay? So take any group element G act on X, it has to also be semi-stable. And this is an if and only if condition. So X is Z semi-stable with a particular phase if and only if every other object G acting on X, all these objects are also semi-stable with the same phase. Okay, and this is actually not too hard to show, which I'll just quickly go through with you. So in particular, one direction is trivial. Going from 2 to 1 is trivial because, well, if all of these are semi-stable, right? If all of these are semi-stable, then we just pick G to be equal to the group identity, and then we have 1. Okay, so one direction is trivial. And for the other directions, suppose that X is actually Z semi-stable. Okay, then we can take any arbitrary Y sitting inside G acting upon X. Okay, So what we can do now is, because we know that G is invertible, I can just apply G inverse. Remember that my action is always going to be exact because it's invertible. Then what you get is exactly as follows, right? Because you now get G inverse of Y sitting inside X. Okay, but we suppose that X was actually Z semi-stable, right? So what we know is that the phase of G inverse of Y must be less than or equal to the phase of X. Okay, they must have the same, they must have, the relation between their angles must be as follows. But remember that we assume that Z was actually G invariant. So the phase of G inverse acting on Y must be the same as the phase of Y, right? In particular, the stability functions are the same. So we have phase of Y is the same as the phase of G inverse acting on Y, and the phase of X is the same as the phase of G acting on X. And therefore, these two things have the same relation. Phase of Y is less than or equal to the phase of G acting on X, and therefore we're done. Okay, so it's very simple to prove in the case of groups. And my claim is that once you have this lemma, then you just need to do slightly more work, and then you can prove that actually it forms a closed submanifold. But now let me just quickly move on to the fusion category case. So if you compare this definition here to the group case, all I've changed is as follows. Instead of a group, I'm going to look at a fusion category C. And I'm going to say that it's C equivalent if for each of my simple object, right? For each of my simple object, my HUD is closed under the action of my simple object. So again, this is exactly the same case as just now. I just want my group action to restrict to the action on the HUD. Here is the same thing. I want my fusion category action restricts to the HUD. And the main changes that I have here is just the following one. I don't just want my stability function to be invariant. I want it to be scaled by what is known as like some sort of a dimension, which we call FPDIM, or the Frobenius Perron dimension of my object. So let me just quickly tell you what this function is. You can actually also think of fusion categories as some sort of vector spaces with real dimension, potentially non-integral. And what I mean is as follows. If I give you an assignment of object into a non-negative real number, and that assignment respects tensor product in the sense that if I take two objects and I tensor them, the dimension multiplies. And it also respects the direct sum, which says that if I wanted to measure the dimension of the direct sum of two objects is exactly the sum of their respective dimensions, then this function, whatever it is, has to be unique. So this can be proven. And moreover, it always exists, and I'll let you think how you should define this. And the hint should be that it's related to Perron-Frobenius in whatever theorem that you know. Okay? So such an assignment is always unique, and this is what is called the Perron-Frobenius dimension. And I want it to be scaled by this dimension. So in the particular case where we have vector space of G greater vector spaces or representation of G, then the Perron-Frobenius dimension by uniqueness must agree with the underlying dimension of my vector space. Okay, it needs to agree with the dimension because of uniqueness. And let's just go back to the case again where we have vec G. And in this case, we have that my Perron-Frobenius dimension of G must be equal to 1, right? Because what is the simple object G? It's just a one-dimensional vector space concentrated in degree G. Okay? And now if I go back to the case where we know, introduced by Macri, Morita, and Stellari, that I look at, instead of G acting on D, I look at vec G on D, you can quickly check that this is actually equivalent to the G-invariant stability condition, right? Because this condition is exactly the same, but with this condition here, FPDIM G is exactly equal to 1. Okay, so we have that it's exactly the same thing as G-invariant stability condition. And finally, just quickly that if you're looking at the Fibonacci category instead, then it turns, surprise, surprise, the Perron-Frobenius dimension of this object is going to be exactly golden ratio. Okay, so the theorem is going to be the same, which says that previously we saw that the G-invariant fixed points forms a closed submanifold. Here we can prove the same thing with together with Dell and Anthony Licata. We can show that the fusion-equivariant stability conditions, which are stability conditions satisfying this definition right here, forms a closed submanifold of the space of stability conditions. Okay, and remember that the proof that we had for groups really uses this invertibility of G in a very crucial way. All right, if you run this proof through, for fusion categories is going to fail exactly at this point. But my claim is that you can actually prove the same lemma with a not so direct proof. And in particular, as far as I know, the proof that I know of uses contradictions. So not very satisfying, at least from my point of view, but it is what it is. And that's how we actually proved it. Okay. So because I'm running out of time, so can I check how many minutes do I still have left? Do I have 5 minutes left?
Yeah, you can go.
Okay, so let me just quickly show you this example. So if you're familiar with pre-projective algebras and stability conditions of pre-projective algebras, or the DG versions or the Calabi-Yau versions, whichever one that you like, then you know that the A4 picture has the space of stability condition is a universal cover of the A4 hyperplane complement. So you playing the same trick again, which is we saw that the A4 quiver had like a Fibonacci category action. And now you instead look at the two Calabi-Yau versions and you cut out this submanifold, the Fibonacci equivalent ones. It turns out that it's going to cut out a two-dimensional submanifold, and that is actually exactly the universal cover of the pentagon hyperplane complements instead. So if you like, quiver theory allows you to study like spaces related to Coxeter and Artin groups. Then if you want to study the non-simply laced ones, meaning the ones where your Coxeter graph has at least some number in it, then you really need the fusion category actions. You need to cook up the correct fusion category actions, which can be done, cut out this submanifold, and that's conjecturally in all cases is going to be a universal cover. In finite type cases, you can really show that it's actually indeed a universal cover. Okay. So about Morita duality and the duality that I talked to you about just now, which is now, remember that now we have two types of closed submanifold. On one hand, if I start off with a group action on D, then here we can study the stability conditions which are fixed under the group action. On the other hand, if I now go to the dual picture, which is DG, so the G-equivariantized category, I claim that there was a rep G action on it. And moreover, now I can cut out the submanifold, which is the rep G equivalent stability conditions. Okay. So something known as a one Morita duality is actually this assignment going from categories which have a G action into categories with a rep G action is actually a true equivalence. It's a result by Drinfeld, Glacki, Nikschik, and Ostrich. In the abelian category case, I won't say too much about what happens if you have a triangulated category instead, but this is known as the one Morita duality, and it was proven for abelian categories. So what's important for us is that there's a very natural bi-adjoint functors relating the two categories, meaning from DG to D, we have the forgetful functor, which just take my object with bunch of isomorphism deltas and just forget the isomorphism delta. On the other hand, you can just take Y in my original category D and make it G-invariant with natural isomorphism by just take direct sums over all possible objects that G acting on Y, all right? Take direct sums over all G acting on Y, and then just associate to it a very natural isomorphism data. And these two functors are known to be bi-adjoints. And this is what we're going to use to cook up a space of stability conditions relation. Meaning, by defining some sort of pullback, which because of time reasons, I'm not going to go through it anymore. By defining some sort of pullback, you can use the forgetful functor and send the G-invariant stability conditions into the stability conditions of my dual category. And this is a close embedding. And this is exactly the result by Markey, Marathon, and Stellari. And once you know what you're looking for, which is just, you know that you're trying to look for rep G, the induction functor just gives you exactly the homeomorphisms that you need. It gives you exactly the inverse to this forgetful functor that you need in the space of stability conditions. And this is exactly the homeomorphisms that we have. Okay, so I've ran out of time, so I'm just going to stop here. Thank you.
Okay, thank you, Edmund. That was very interesting. Okay. I leave time for questions if you want.
Hi, I have a question. Very nice talk first. Thank you very much. And you talking about actions of fusion categories. It seems like maybe you can try to see the actions of non-fusion categories, just tensor.
Yes.
Yeah, you use that in some definition you use that something works for all reducible pictures. So maybe there's the problem. I think it works. So do we have it?
Yeah. So let me say a few things. So my expectation is that you can throw away fusion in this and go to finite tensor categories. Okay. So at least in terms of definition, everything seems to work. I still know what my performance dimension means. And the only thing that I can't prove somehow is this thing, which is the main lemma that I mentioned just now. This guy right here. As far as I can, again, don't take this too seriously, because what I'm claiming is that my proof doesn't work because it's a proof by contradiction, right? I mean, I'm not saying that if once you throw in a non-simplicity, everything's going to break down. My proof breaks down. My contradiction breaks down. So my assumption is that finite tensor category will work. But the other picture, which is, let's just say that now we don't look at finite tensor category, but instead throw away finitely many symbols. So for example, look at a semi-simple Lie group, right? With infinitely many simple objects. Then I'm no longer so sure. So first of all, maybe in semi-simple Lie group for rep of the Lie group, then you can still have no nice notion of dimension because of vector spaces. But in general, I'm not too sure. So it needs to have some sort of, at least some nice structure. So maybe something like limits of finite tensor categories, then that will still work. But I think that's the direction that one can do. You can kind of cook up either finite tensor category or limits of finite tensor category, and most of these should probably still work. But I should also say that I just don't have too many interesting examples other than, you know, Lie groups or something else. I don't have interesting finite tensor categories on interesting categories yet, and that's the only reason why I haven't looked into it. But maybe what one can do is look at how I prove this, see where I use semi-simplicity, and maybe there's a nice way of making it work without the semi-simplicity assumption. So yeah.
Thank you very much.
Okay.
The other questions?